Good afternoon, everyone. I'm August Cruzy, the CTO for Big Shine Energy. We are a full turnkey sustainability solutions provider for commercial, government, institutional, and industrial building operators in the US, Canada, and even in the Dominican Republic. Today, we want to share what we've learned about a hidden part of our buildings that is a critical foundation for sustainability success. Because it is hidden, it is almost always neglected. The foundation that I'm referring to is the grounding electrodes and wiring inside our building's electrical system. So why do we say this is the most overlooked building system? Let's take a look at what we'll be learning about today. Grounding is an essential but hidden part of our building's electrical system. And what was okay in the past is not okay today. And it's because critical building systems are now full of semiconductors and electronics. The performance of the grounding system is dependent on proper wiring throughout the facility, including the exterior wiring. And maintaining a low resistance to earth ground is very essential. We'd like to see that always be at least below 25 ohms and preferably below 5 ohms. This is a requirement that there's no fixed perfect number, but the lower the better. The grounding resistance is strongly affected by seasonal and climatic conditions. Grounding should be verified by testing at least every 3 years, and preferably every year. And also, there's something that we can add. It's called Type 2 surge protection devices. They're now actually required by the National Electrical Code, and they play a valuable role in protecting critical building systems, but not everybody is aware of them. So we're going to start out with a picture. Here we see our conference room, and it's very bright with LED lighting. So LED lighting and controls is what we call the low-hanging fruit of sustainability. It's a great way to not only save energy, but to upgrade your facility so that you get tremendous benefits in productivity and wellness, even with your workforce. You notice here that we mentioned something called the CS, or circadian stimulus. And this is something that's important to know about because it can help all of your employees be very alert and bright during the day when they need to be working. And then later, they'll be able to get a good night's sleep. But we want to think about our foundation. This is the most important thing. But I'll start this presentation with a few snapshots of places where we've used this low-hanging fruit of sustainability, LED lighting, to brighten up our workplaces and also our play spaces. So as you can see, LED lighting is really essential for any kind of modern facility that we want to enjoy, especially if we're going to, for example, televise sports from a facility like this. But we may work in a warehouse. In this case, it's very important, both for productivity and for safety, to be able to clearly see what we're doing, but to be able to save energy at the same time. But all of these LED lights that you see, they're full of electronics. Each fixture has an electronic driver, which converts AC to DC. And it's very sensitive, therefore, to bad power quality. Here's the Yogi Berra Stadium at Montclair State University. And the lighting here was improved by LED lighting, so much so that they can now televise sports events there. But also they're saving over about 150,000 kilowatt hours a year with LED lighting. So you get better lighting and less energy cost. So today, wherever we work, whatever our workspace is or our play space is, it can be enhanced and upgraded not only with LED lighting, but with all kinds of other systems. But these systems work behind the scenes. Let's take a look at what's actually behind all of the things in this office. Well, down in the mechanical room, we have HVAC systems, and we want to replace the old high pressure sodium lights with LED lighting. But we may also be going in there and replacing variable speed drives and adding direct digital controls of our HVAC system and building management system connections. There's all sorts of electronics now in our HVAC equipment. And then we may be adding a solar PV system and battery energy storage or sub-meters. Our buildings are now full of electronics, but they're all behind the scenes. And so it's easy to forget about them. It's easy to forget what they need how we should feed them with good power quality and not with rough, inconsistent power quality. So today, there's all kinds of things that we're under pressure with, and we want to be able to optimize our operations. For example, demand charges. Every 15 minutes, the utility will typically monitor our kilowatt demand, how many kilowatts we're drawing, and then that one interval per month that hit the peak will be charged a cost based on that, and that'll be added to our consumption. So we need sub-meters, and even we can use AI and building management systems to limit that demand charge. And also, if we have a smart building and smart factory or smart plants, we're going to be full of data and full of controls. There's all kinds of systems operating 24/7. So we may need sub-meters to monitor those. And it's also critical that we avoid unplanned downtime. We can't afford to have this equipment go down. And as you know, the more equipment that we have, the more complicated it is to maintain it. It takes a lot of management time when there's something that goes wrong unexpectedly. So Big Shine Energy, we have the solutions. Here you see a histogram of the kilowatt hours that were saved just through a LED and controls lighting upgrade. You can see that it saved hundreds of thousands of kilowatt hours each month. If you compare the blue histogram, which was the previous year with metal halide lights, and the orange to the LED. But also we can provide power quality and energy meters. We can provide AI software and building management systems. We can install wireless sensors. We can install HVAC and VFD upgrades, and also solar photovoltaics, battery energy storage systems, and EV charging. But all of these gadgets, they can greatly improve our operations and cut our costs, but they all have one thing in common: they're full of electronics. So I want to make an analogy. Our aging electrical infrastructure, and this is not just the infrastructure outside our building, it's also inside our building. These can be stones in the road to sustainability. So let's draw an analogy. It's not illegal to drive an old car. Well, this thing is a beauty. I'm sure you'd feel kind of excited to go cruising around in this. That would be kind of a blast from the past. But what does this car not have? Well, it doesn't have fuel injection, collapsible steering column, anti-lock brakes, shoulder belts, airbags, head restraints. All of these things we take for granted today. None of those existed back then. And of course, this was a gas guzzler, and it ran on leaded gas. So of course, it made sense to go with the new technologies and to keep upgrading year by year in the kind of things that we could offer to our customers. But I want to make sure to point out that grounding and power quality, they're not just a problem for old buildings. Not all buildings were built in the 1950s. There's plenty of modern buildings. But what's surprising is that buildings built even in the last 10 or 20 years were typically built to codes which do not guarantee good power quality, because the codes haven't focused on power quality. And also, even master electricians, they don't receive training in best practices for ensuring power quality and protecting today's electronics. That's not part of what the electricians' training has and requirements have been focused on. Now, I will say that data centers and telecommunication hubs, they are built with excellent grounding systems and power quality. It's because they have to. They have no choice. So you will find good grounding systems and good power quality inside those facilities. But for all the other facilities out there, there's lots of buildings that, even though they're very modern, they may have been through renovations, there may have been equipment replacements, they may have been repurposed, there'll be random maintenance. During all of this, mistakes can happen, connections and wiring can corrode. And also, as I've mentioned, even the recent codes didn't necessarily guarantee good power quality, because that wasn't the purpose of the electrical code. So let's remind ourselves, what was the purpose for the NEC, that what we call the code? Well, it originated in the 1930s, and it provided for life safety and fire safety in electrical systems. There was no provision for electronics because they didn't even exist back then. So it was never intended to be a best practices guide for electronics. Sustainability retrofits and new construction, what do we see now? They're now all electronic. Just about everything has a computer or electronic power supply. We're converting DC to AC and then from DC back to, or AC to DC. All of these things are taking place all the times in our buildings today. Now, in recent revisions of the code, many articles were added to require surge protection devices at the distribution or branch circuit panels because it was recognized that voltage surges and voltage disturbances were damaging many systems that are essential to business continuity. That can include fire safety, industrial safety and controls, elevator controls, communications, and data processing. But not everybody is upgrading to the latest code because legally they may be allowed to think, well, we're grandfathered in. But actually, that's not a good way to think in today's world. We should always think, what does my facility need to be working at its best? Also, the IEEE, the NFPA, and NEMA all have additional recommendations about grounding and related protections for electronics. Now, here's one example. This is just a facility that we serviced. And as you can see, it has modern electrical distribution equipment. Siemens is a very good manufacturer. They make excellent equipment. And this building has what's called a TVSS, a transient voltage suppression system. This is what we would call zone 1 surge protection because it would block very high surges of electricity, of voltage that would be coming from outside the building. But 80% of the electrical disturbances that damage electronics are actually originating inside our buildings. And this doesn't really do anything to protect against that. Its only purpose is to block really big disturbances that come from outside. So let's take a look at another anomaly with this system that wasn't illegal, but it's not best practice. Here you can see if we were to scan over to the corner of that array of electrical equipment, we would see heavy cables going up to one of the I-beams in the building. So here, this is the main building ground, and it's connected through the building steel, as we call it. In other words, the ground doesn't go directly to the earth, it goes into the steel structure of the building. And so it, first of all, makes it difficult to measure the building grounding with that kind of system, because if you put a meter on there, a clamp meter, and I'll show you the type of meter that we use, it's made by AEMC, it'll indicate loop when you try to read resistance, because the signal will just go up into the building steel and come right back again. It never went into the ground, and it can't tell you what the ground resistance actually is. So why building steel should not be used as a primary grounding conductor? This company, ES Grounding Solutions, is a company that does grounding surveys, and they install upgraded grounding equipment. And on their website, they put this notice: when using the building steel as the grounding electrode, electrical noise, harmonics, and magnetic issues can occur. All of these can adversely impact the performance of electronic components. So here you can see that there's not supposed to normally be a lot of current flowing through the grounding system, but there will always be a little bit. And when there's a disturbance of some kind, then there will be a little pulse going through the grounding system. But here, that pulse doesn't go directly into the earth ground below the building. It goes up into the steel structure of the building, and that's what this website is referring to. This is not good for electronics. It's good to review, why is there a building grounding system in the first place? The utility has to ground their system at the transformers outside our building. And that's to make sure that there's a stable reference for the voltage going into the building, and also to bleed off disturbances such as lightning strikes. But inside the building, there's an additional requirement. There's actually two requirements. One relates to safety and fire protection. If there's a short circuit somewhere where the insulation on a live wire becomes damaged, and that energized wire, the metal conductor inside the wire contacts the frame or piece of equipment, we want the resulting fault current, as we call it, to have a path back to the source, meaning back to the distribution panel, so that the circuit breaker can trip. That's why we have circuit breakers. They trip and open the circuit when there's a sudden rush of current, meaning there was a short circuit or a fault of some kind. And that prevents people from being shocked, electrocuted, and also prevents arcing, which would start a fire. But the grounding conductors run all throughout our buildings for this purpose, and they're connected to every piece of equipment. Now, some branch circuits and some buildings, they don't have copper conductors running with the power conductors for ground. Sometimes they use conduit for the grounding circuit. And then when there's conduit, these are like long, thin lengths of pipe, steel pipe, and they have couplings. Every so many feet, they put a coupling. Over time, if the couplings corrode or they become loose, or there's a little lock nut at the box or panel that becomes loose or corroded, then the resistance of that ground circuit can increase. So all of those are things that need some maintenance and some inspection. Also, grounding conductors provide a path to get rid of voltage spikes that may be created inside our own building for power quality. So the grounding system performs an essential role in reliability for all that electronic stuff that we're adding to our buildings today. So what kind of building equipment needs good power quality? And by the way, I should say that poor power quality is something you won't see with your eye. You won't know necessarily that it's going on, but I'm going to show you some waveforms that were captured with a special meter in a few minutes, and you'll get an idea of what bad power quality looks like. So every type of control, elevator controls, building management systems, all that IT stuff, computers, servers, routers, the fire alarm and emergency systems, battery backups, HVAC equipment with direct digital controls and VFDs, medical imaging systems and laboratory equipment, CNC or automated robotic manufacturing machines and equipment, and finally, LED lighting. All of those need good power quality, and all of those are sensitive and will have shortened life if the power quality is poor, or if the grounding system especially is poor. So how does bad power quality cost us money? Sometimes, again, because it's going on day by day, but everything's working, we're not aware of the waste that we're experiencing on a regular basis. When there's distorted power, everything runs hotter than it should. Our computers, our motors, our transformers, all the electrical equipment we have, it tends to run a little bit hotter. And heat is an accelerating factor for shortened life. So whenever things run hotter than they could otherwise, they're going to have a shortened life. That's just a kind of a rule of nature, that the insulation and the bearings, everything inside the equipment, all is affected by heat. So what's going to be the consequence of that? Well, first of all, during the summer, if we have equipment that's running hotter than it needs to be, we're going to pay money right away with the higher cooling load. We have to cool off the building to keep everybody comfortable, but now we're cooling a bigger heat load inside the building than we otherwise would have. But then also, if we shorten the life, out of the blue somewhere, a motor will fail, or a server will go down, or a transformer will go bad. It's not very often, but these things become very expensive and they're big disruptions to our operation. So 3 and 4 are meant to indicate both the direct and the indirect consequences of unplanned outages and premature failure. And then finally, demand charges. As we saw, if everything's running a little hotter than it should, it means we're drawing more power than we should. So month after month, we'll pay a little bit more for those demand charges, so many dollars per kilowatt of demand. And also, we may pay more money for power factor penalties. So very often, utilities will require a penalty, a fee, if our power factor drops below, for example, 0.9. So all of these things are affected by power quality and efficiency, and therefore we want to optimize our operations. I wanted to talk briefly about 2 different ways to meter power, and one is really for energy monitoring, and the other is for power quality monitoring. So there's two different types of devices used for that. Wireless current sensors are very handy devices, and they're very powerful. There's a lot you can do with them. So for example, you can put these throughout your facility and you can use it to monitor specific loads, and it will send a signal at a periodic interval to tell you how many amperes of current are being drawn. If you have a three-phase system and you want to make sure that all phases are balanced, you can use a three-phase version of that. So the little blue dots on this line chart are meant to indicate the typical sampling intervals, meaning that the fastest one I saw in the market was every 10 seconds. It will send a signal saying, this is how many amperes I'm measuring. In between, it doesn't record anything. It just sends a blip, blip, blip. The next fastest was every 30 seconds. After that, 1 minute, or after that, 6 minutes or 10 minutes, and some are like 30 minutes. So it means that you're going to get a snapshot in time periodically, and then somewhere else in the building, you have to intercept those signals, you have to receive them, and have some kind of software that analyzes that and tracks it for you. Now, if you get a disturbance, I mentioned that I would show you waveforms to show you what bad power quality looks like. This is a single phase that I'm looking at. The meter was measuring all three phases, but I just took a snapshot of one phase. And if you look at the crest of the sine wave to the left, you can see that it's all irregular and spiky. It shouldn't look like that. That's ring transients and impulse transients, which are very almost instantaneous little spikes in voltage, and then they come back down. But then there was a sag. Something started up in the building. Maybe it was this device that this was connected to, this phase, and it pulled down the voltage for a few cycles, and then the voltage rebounded. And for a moment there was some irregularities and a little bit of harmonic distortion. But this whole event took place in about 0.42 seconds, less than half a second. So it means that with these wireless current sensors, you're never going to see things like this. You won't have any idea that they're happening. They're just telling you an RMS value at a point in time, and unless it happens to exactly coincide with a big disturbance, you won't even know that anything's happening. And I want to show you also that this spiky stuff here, which is very damaging to electronics, has very little signal, or it's very hard to detect with, say, an electrician's voltage meter. Here we were sampling at 512 samples per electrical cycle. And actually our power quality meter, we can increase that to 1024. So here's some examples. One of the companies that we use is Electro Industries. They make sub-meters and power quality meters. And we made this little comparison chart that can show you, don't hold me to this. I just copied this, tried to extract this from their website. But if you're interested in checking out their meters, please go directly to their website and do your own research. But this was just to give an indication that there's a lot of different capabilities out there, but you do need to check, what do you want to do? Do you need a time of use meter? Are you going to be doing advanced power quality logging or only intermediate logging? Do you want to have Wi-Fi capability? Do you want to be able to get email alerts? Different meters have different capabilities. So why is building grounding so important now? Well, the fundamental reason is that in the past, legacy electrical systems didn't really anticipate the proliferation of modern electronics, and they're not protective of them. So for example, just to cite the example of lighting, all of the commercial lighting out there before, metal halide, fluorescence, they were not very sensitive to impulse transients, the kind of spikes I showed you in that waveform. But in contrast, every LED fixture now has a precision electronic power supply called a driver. That driver has to take AC power at a high voltage level and convert it to a very low voltage DC, which is carefully regulated. And that's not easy. And if that the electronics in there are vulnerable if there's a lot of disturbances on the power supply, on the power equipment. So what we do is inside the driver of every LED fixture, there is a surge protection device, and it becomes conductive when the AC voltage exceeds a preset threshold. So that means there is a little protective device inside every one of these uh, devices, whether it's an LED driver or any of the other equipment, a VFD drive. They all have some sort of circuit protection, but there's a limit to uh, how many times you can hit them with impulse transients or spikes. In addition, for them to work, they have to be connected to a low resistance ground path because the surge protection device built into your equipment has to send that little voltage spike somewhere. And the place it wants to send it is to the ground underneath your building. It can't do that if the resistance is high. Now, the NFPA and the IEEE both recommend that this should be less than 5 ohms. There's a sort of implied requirement in the National Electrical Code to be less than 25 ohms. But even there was a loophole, and I'm going to explain about that in a minute. By the way, the Institute or International Agency of Electrical Inspectors, they recommend that you test your system at least once every 3 years. This is the loophole I wanted to mention. In the National Electrical Code, and I think this is true even in the latest versions of the code, they had a provision that if you put in a driven rod grounding system and you measure the resistance, it should be less than 25 ohms. But then they put this very strange loophole in there that if you got a reading above 25 ohms, all you had to do was add a second rod a certain number of feet away, but you didn't even have to test it after that. So if you just added a second rod, who knows what you got? You weren't required to test it. So this is why I say even buildings that were built recently, there are some things about the electrical system and the electrical code that allowed some bad stuff to happen that's not really optimum for keeping our electronics working for the way we want them to. We can't have sustainability success if we have electronic equipment being fried periodically. Here's some examples of waveforms just to give you a visual of what certain types of power quality problems look like. So this little sine wave, classic sine wave up on the right, that's what electrical AC power should look like if you look at it with a certain type of meter where you can look at voltage versus time. It should be nice, smooth sine wave. But if you look at the actual waveforms that we've measured at some of our customer facilities, you can see that it's like horribly distorted. This is what we call harmonic distortion. Now, what causes the voltage and current waveforms to become distorted like that? Well, anytime we chop up the power and take AC and convert it to DC, or take DC and convert it back to AC, we're going to get harmonic distortion. So just about everything we do, there's so many different devices throughout our buildings and our plants and our laboratories, our hospitals that are doing these things all day long. So keeping control of harmonic distortion is not easy. And it does have an effect on both our equipment and also the costs, as I showed earlier. Here's another waveform. Now, if I took an electrician's meter and put it on this circuit, I would measure a line-to-line voltage, as you see in this little gray box here, VAB, from phase A to phase B. I'm measuring 491 volts, 491.37. It nominally should be 480. So you might think, oh, it's a little elevated, but that's not a big deal. It's not, the percentage-wise, it's not a big change from the nominal. But if I look at the waveform with a high-speed meter that's recording hundreds of samples per electrical cycle, then I see something that looks ugly. And as you can see, the crest, there's all these different repeating transients. And also the actual peak voltage is much higher than the nominal peak voltage should be. So that's what you want to focus on. Your electronics were designed for this black dotted line at 393 voltage. That's for a nominal 277 volt circuit. The peak to peak would be 392. But we're getting way up here, well up into the 400s, and then there'll be impulses that'll be up over 500. Here's an example where you can see those impulse transients. So ironically, the electronics in our building are creating these disturbances in many respects, and they're also the victim of these disturbances. Because these impulse transients and ring transits happen almost constantly in many facilities, this becomes what we call death by 1,000 cuts, or maybe literally death by 1,000,000 cuts, that the electronics can take it for a while, but over time, it can only be hit so many thousands or millions of times, and then eventually it blows a hole in a circuit somewhere, and then your equipment fails. This is also another view to give you an idea of ring transients. That's like a very rapid ringing or oscillation. Here you can see that there were 12 seconds or 12 cycles of up and down for the phase C to neutral current or voltage that are occurring in 1.5 milliseconds. That gives you an effective frequency of 8,000 hertz. But the control circuits in a lot of our equipment is designed for 60 hertz power. So you can see it becomes hard to control it, to regulate it, and it's hard to protect against these spikes that you see. Now, one of the problems that we have is that soil conditions and age and corrosion all take their toll on our grounding systems. So even if our building had a great grounding system when it was new, it may become not so good and may become totally inadequate due to all of these factors: age, corrosion, and soil conditions. So here, this happened to be a commercial building, which is a little surprising. And they actually had a driven rod grounding conductor outside the building, but it was exposed, which makes it very vulnerable. And you can see it's completely corroded. And if we look at our AEMC clamp meter, we can see that we're getting a very high resistance, 365 ohms. So that's useless compared to a practical, I'll call it a practical requirement to be less than 25 ohms. Even if it was allowed, if this was a redundant or second grounding electrode at this building, it's doing nothing for you. So one of the things that AEMC Instruments, which makes the meter that you just saw and makes many other types of grounding meters and power quality meters, they are experts in grounding, and they do a lot of training in how to do grounding assessments. So I did just a little notional sketch here with AI to say, okay, what's happening to our buildings if the soil around them, we're having one of those summer heat waves? Nowadays with climate change, we're seeing more extremes. There are times when there's extreme high levels of water, with these atmospheric rivers, but we also see extended periods where it's very hot and very dry, and then the soil dries out to a great depth. So if you look at the values of soil resistance here, this is from the AEMC website, from one of their publications. They say that sandy loam with a 20% moisture content has a resistance of 6,300 ohms per centimeter. But at 2.5% moisture, what happens to that resistance? The 6,300 jumps to 150,000. So also temperature is a big factor. If you have a nice 15.2% moisture sandy loam and has a resistance at 20 degrees Celsius, what we would call roughly about room temperature, 7,200 ohm centimeters, what does it do when it's cold at 23 degrees Fahrenheit or -5 Celsius? It jumps to 79,000. So it means that if we measure our resistance of our grounding system at one time of year and under one set of sort of climate conditions, if we measure it months later, it may be totally different. This is a curve, again, from two curves from the AEMC brochure, Understanding Ground Resistance Testing. If you look at curve one, you can see that there's a significant variation in climate in of the months of the year with the resistance that they obtained with a 3/4 inch pipe in what they call rather stony clay soil. And most of the year it's failing. There was one brief interval, the month of May, where it was like barely okay. And then curve two, you can see they got a very low reading in May. So if you measured it in May at that year, you would say, wow, this is a very good grounding system. But look how it does in November. and December and January. It's terrible. So it's really important that we understand these relationships so that when we do test, we can interpret the results correctly, because what matters is not whether we can say, oh, we did the test and it passed, but that's passing today. What we want to do is have a facility that's robust and we have sustainability success. Now, AEMC was very kind, and they allowed us to use the next 4 slides, just to illustrate that there's a regular system that they provide, a calculator for calculating soil resistance. And so they also give training. Here they're using the training in a residential setting, but this is also done in commercial facilities. And so with some simple measurements and their instrument, their ground testing, the soil resistance and the grounding resistance can be determined very accurately. And also they train all operating personnel in how to do this. So that it's very easy to learn how to become competent in ground resistance testing. So what can a facility grounding study consist of? This is not like comprehensive, but it's just to give you an idea. So first, testing the earth ground resistance of the main building ground at the service entrance. That's sort of your benchmark. Also, we like to measure AC leakage current on the main building ground and also on the ground conductor at each distribution panel, because there is normally a little bit of what we call leakage current, because the wires throughout the building, they have voltage on them, and there's a little bit of capacitive and inductive coupling or connection, if you could say, between them. But the amount of leakage current should be fairly small, in the few hundred milliamp range typically. But if you see a big number, like over 1 ampere, something's probably wrong. It may mean there's a wiring mistake or incorrect wiring connection somewhere in the building, typically a neutral to ground connection where there shouldn't be. Another important thing to do is to do point-to-point resistance testing of the branch circuit grounds. That just verifies that for safety reasons, especially, but also for the life of your electronic equipment, that you may have a great main building ground, but what if somewhere there's a break or a loose connection in the grounding circuit and you don't get a good ground from the equipment back to your main panel? Then if you have DC equipment, DC charging systems, battery chargers for forklifts, inverters, solar PV. You can also measure DC leakage current if you have the right type of clamp meter. And then this is not part of a grounding survey per se, but we think it's important to do. And that is to check the ratings, which can include the maximum continuous operating voltage, and there's several other ratings that should be checked, of the type 2 surge protection devices, which are installed on all branch circuit panels having electronic loads. And if you don't have type 2 surge protection, we recommend putting it in. It's really important. And then depending on the facility, you can also test soil resistance to correlate it with your main ground resistance. Now, we find all kinds of problems out there when we do sustainability upgrades at facilities. Very often there's been a problem, but nobody really recognized it as a problem. But then when we install brand new equipment, if there's some kind of an issue, then it kind of comes out, oh yeah, we did have a problem now and then. For example, this is a little piece of wire that we had to take out of a lighting pole for area lights. And you can see that the insulation was damaged and the copper strands inside the insulation that was then broken or cut has been arcing periodically against the inside of the metal pole. But because it didn't contact the pole continuously, it just every now and then there would be a trip breaker. But there's a tendency when that happens for the operating personnel to sometimes say, oh, well, and they just reset the breaker. And then because this is an intermittent fault, usually nothing happens for a few months until the next time that it trips again. But we really should think nothing happens for no reason. So if there's an occasional circuit breaker trip and you don't have a reason why it happened, it's really worth taking the time to investigate. I want to talk specifically about area lights because there is a problem. Mike Holt, the electrical code expert, has spoken very passionately about this issue. And that is that it used to be acceptable practice to assume that the fixtures and the pole itself were grounded through the base of the pole. But this turns out to be a faulty assumption because if there's a fault, in order to trip the circuit breaker back on the circuit panel, which might be inside the building, the fault current, what we call the current from the short circuit now to the pole and then therefore to the base of the pole, had to make its way back to the electrical panel through the dirt. In other words, possibly through hundreds or even thousands of feet of dirt. That resistance is so high that very often the circuit breaker would never trip. So the pole would actually be energized. Actually, the city of Palmdale, California, ran into this problem where they did a whole lighting upgrade in the city. And then they had to announce, it was published in the LA Times, don't touch the poles when it's wet outside because you might get shocked. So I'm going to take a look at, we're going to show some different wiring schematics, and we've actually seen every one of these. And it's something that's surprising because you would think that this is something that shouldn't happen today, but it's the way things have been. And it's part of this inertia that old codes that really weren't effective have been allowed to be used and relied on far beyond their original purpose, or maybe they were never that good. So let's take a look at some schematics. Here we show a distribution panel. We've got 3 phases, A, B, and C coming out, and it's grounded. The panel itself is grounded, but there's no ground connection that directly connects from these poles or the base of the pole back to this panel. The only connection would be through the dirt. So this is the situation I was talking about, that if one of these green grounding conductors were to have a fault, or let's say something short-circuited inside the light fixture, you're probably not going to trip the breaker and the pole might be energized. This is also terrible for power quality. Then, you could have many of them connected together and then to a common connection to the pole. There might be a daisy-chained wire grounding conductor from pole to pole, but here you still don't see a path back to the source. So we've seen all of these different variations. And so it's very good if you have concern to get your maintenance team to just check this out and say, make their own schematic and show you what you actually have. I did mention earlier that one of the things we can do during a grounding survey is to test for leakage current on a ground conductor. Because really the ground conductor should not routinely have a lot of current passing on it. But here you can see this, our AMC clamp meter around this braided or this heavy copper wire conductor, grounding conductor, has almost 4 amperes of current on it. That's a sign of problems. It shouldn't be, if we see more than 1 amp, automatically we assume this is something that should be investigated. And very often we find that inside a distribution panel, or even inside a specific piece of equipment, there's a connection where neutral and ground were connected, where they shouldn't be. There are a few places in a building where the neutral and ground must be connected according to code, but everywhere else in the building, according to code, they must not be connected. What's one of the solutions to all of the issues that we've seen here? Well, one of the things we should do right away, even before we complete our grounding survey or with our grounding survey, is to install type 2 surge protection if we haven't already done so. And we use 2 very excellent companies for our type 2 surge protection. One is Transient Protection Design. They make a surge protector that has what they call enhanced sine wave tracking. And basically, it's a type of filtering that filters out all of that spikiness that you've seen in those waveforms that I showed you. And that's very important because that's what we need to protect electronics. If you put one type 2 surge protection device on a given panel, it will protect all of the electronic loads on that panel. The only requirement is this transient protection design device does have to be connected to a very effective earth ground. If there's a concern about the ground and we can't verify it, there's another device that we use. It's made by a company called MaxiVolt. This has a very unique feature called a hybrid surge suppression circuit, and it doesn't require a connection to ground. So it's able to suppress these spikes and voltage disturbances, even if the ground isn't adequate. So MaxiVolt is a great way to take care of a system that we can't verify or we don't have time to verify that the grounding is effective. Now, I did mention that the National Electrical Code is starting to catch up with requirements for Type 2 surge protection. And here on the screen, you can see some of the relevant NEC sections, but you should do your own research. Just take this for education purposes. And then also see the sections and these subparts of NEC 250 that talk about the effective ground fault current path. And this is where you'll see that it's no longer adequate to just rely on the dirt to be between lighting poles, for example, back to your source. So let's recap what we've gone through here today about grounding. And first of all, I want to say, I hope this isn't overwhelming. It's really not meant to be. It's just meant to be something that's, because it's a foundation and because it's hidden, it's really essential, but it tends to be neglected. It's not really that hard to inspect and to upgrade, take care of any issues that you find for the most part. There may be some issues that will be a little more substantial, but it's better always to know about them and to mitigate them step by step. But especially what was okay in the past is not okay today, because all kinds of critical building systems that we rely on and that we're getting value from are full of semiconductors and electronics, and they're very sensitive to the kind of power we feed them. And also for safety. If we have an unsafe system, that's a terrible situation, and we don't want that to persist. The performance of the grounding system is really dependent on proper wiring and connections throughout the facility, and especially the exterior wiring, because so many things were allowed in the past that weren't good, and maintaining a low resistance to earth ground, meaning less than 25 ohms year round. And we'd really like to see that be less than 5 ohms. So as you saw from the AEMC data, grounding resistance is strongly affected by seasonal and climate conditions. And so what should we do? We should check our grounding at least every 3 years, and preferably every year. If you've never done it, and we find a surprising number of facilities have never done it, it should be done. And then also, we really strongly recommend Type 2 surge protection devices. Even if legally you can say, well, we don't have to comply with the latest version of the code, we're allowed to use the older version of the code, that's still not going to help you if you have equipment go down, or if you have some sort of dropouts of data or whatever it might be due to poor power quality. So we talked a lot about building grounding systems, Type 2 surge protection, measurements, and so on. But I just want to close with a few fun pictures that at Big Shine Energy, we do BMS and we do HVAC. And we're very happy to work with you on any kind of upgrades that you'd like to explore there. Also, we do solar PV, and battery energy storage systems. And we're, again, very excited because this is a great technology, very important for sustainability. And also, we do EV charging stations. So if you have interest in any of these sustainability upgrades, please talk to us. And by the way, we do all this work with grounding and power quality because we want our installations, we want your sustainability upgrades to be successful. We don't want them to be a headache, that after a couple of years or even less, there's starting to be problems because the building facility was never set up for it. It's usually not that hard to get it tuned up. Also, we do energy audits, ASHRAE level 1 and ASHRAE level 2, and we can do level 3 also, although those are less common. But I wanted to mention briefly about what is the skill set needed to do today's energy audits and energy conservation upgrades. So there's several certifications that are very valuable and very important. The AEE Association of Energy Engineers has several certifications, including Certified Energy Auditor, Certified Energy Manager, and Certified Building Commissioning Professional. Also, the ASHRAE has one called BEAP, Building Energy Assessment Professional. And then there's Niagara certification for if you're looking for building automation system or building management system upgrades or installations. NABCEP certifies for PV, photovoltaics, or solar system designers and installers. And then even for battery energy storage systems, there's not a universal certification, but there's one called STEM University. STEM is a very excellent provider of battery energy storage systems, and we've participated in that. And then Cisco and Lighting certified, but also IS Networld, the one in the middle there. This is very important because to have contractors come in and do major projects like this on your site, whether it's audits or grounding studies or actually installing all this upgrade equipment, you want them to be safe. And the IS Networld is a very important safety certification. At Big Shine Energy, we have members who we have at least one member for every one of these certifications. And for many of these certifications, we have a number of different members who have, for example, CEA or CEM, whatever it may be. So thank you very much for your attendance today. We know we threw a lot of information your way. It may be a little overwhelming, but it's really not meant to be. And actually it does break down to be just a few very important principles. But if you would like to get in touch with us, this webinar has been recorded. And so we can't answer questions live, but please reach out to us. We would love to work with you. We're really devoted and we're passionate about sustainability, and we're willing to go that extra mile to do everything, including making sure that the foundation is in perfect condition for your sustainability upgrades. So thank you so much for your attention and have an awesome day.